Okay, it's time to look at 2D kinematic problems and the very basics that we need to start setting these problems up with. We're still going to use our kinematics formulas, our 1 through 4 formulas, and they still have the same stipulations that make them each one special. But we're going to need to figure out how to change them up ever so slightly because things are a little different in 2 dimensions. What do I mean by this? Well, in our traditional 1 dimension problem, right? We had just a scenario like this where you're firing something straight up. We'll just make it a ball in this case. And so we only had to worry about it going in 1 dimension. Even while doing that though, we had 6 different variables. We had a initial velocity, a final velocity, a time, a initial displacement, a final displacement, and an acceleration. And so we had to learn everything we could and then solve for the rest of these, right? Well, that was a 1D problem. When we have 2D, then we're talking about a scenario where you have something like a projectile being fired at an angle. Because it's being fired at an angle, it's going to be moving up and to the side. So that means we need to define our axes. We're going to have our x-axis in the horizontal and our y in the vertical. You can define them however you want, but it's good to go ahead and define them. Part of the defining is to say that they're positive in the up and positive to the right. That doubles up the amount of variables we're going to have because now if you think about it, we have these for every direction. So let's write those. And so now you can see that for my y-axis and my x-axis, I have all 6 variables again, but I put an extra subscript designator. So now I have things like my initial velocity in my y and my final velocity in my y. And this becomes very important, but we can reduce this. So how do we reduce it? We use some super common sense powers, such as if it's 1 projectile, then my time in going up and over always have to be the same. It can't be at one place vertically and a different place horizontally in time. So that means we can write an equivalent statement saying that Tx is equal to Ty. And then we don't even have to worry about that anymore. We can just say that it's time in both. The next thing I want to look at is most of our problems are always going to be happening on Earth. If they do, then we are a constant acceleration, but that acceleration is something that's known. It's gravity. And gravity doesn't operate in both directions. In fact, gravity only pulls things down. So as long as our y is in the up and down direction, then that's what our acceleration is going to be. It's going to be negative 9.8 meters per second squared. This does 2 things. It gives us a value for y up here, our acceleration in y up here, but it also tells us that if that's the only thing accelerating that projectile, then I don't have an acceleration in my x, that my acceleration in my x is just going to be 0 meters per second squared. And if it doesn't have an acceleration, then that means that my Vix and my Vfx are equal because we know that it's not accelerating, which also means that it's a constant velocity problem instead of a constant acceleration problem. Okay, now that can only be assumed if, like I said, our y direction is up and down. We are on Earth, that's gravity, and there's nothing else accelerating our projectile. So if it has a rocket or something like that that's propelling it, that's constantly accelerating it, it might have an x. But for our sake, we're looking at simple projectiles, which means as soon as it leaves its source on the ground, it has all of the acceleration in that direction that it's going to have, and the only thing accelerating at that time is going to be gravity pulling it down to Earth. One of the next things we'll need to set up a kinematics problem like this is more than likely this initial object is going to have an initial velocity, and it's also probably going to be set at some sort of angle theta. Now, this can't be used as it is. It has to be broken into its components parts, which means we're going to have to use that vector solution we had before, where we had VI and a certain angle theta, and it's going to be equal to its vector components. So it's going to have a component of VI y and VIX. Now, hopefully you remember how to do the trig. Just remember, and I guess we can take a small second to look at that. So remember, in trig, we have sine of an angle, cosine of an angle, and tangent of an angle, and they each equal something. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. And we can solve these, especially sine and cosine, so that we can make it easier for just getting that opposite side. So we can solve this to the hypotenuse times sine of theta is going to equal just the opposite side. And in the same way, we can convert cosine to hypotenuse times cosine of theta is equal to just the adjacent side. And that's all I'm going to look at right now, because that's all we need for up here. And so you can see you can get your different component sides by doing that initial velocity in a odd angle, and do VI times cosine of theta to get our x, and VI times sine of theta to get our y. And that'll give us two of our different components in this, and they'll probably be different values, but it's how you would solve that. Okay, the last thing I want to look at about this is in this trajectory, right? Let's assume a very simple trajectory where it goes up at an angle. It's going to make a parabola. It's going to start at one point and end at the same height, okay? With that, notice that it's very symmetrical. Because of that, we can assume a couple of things. One, in the y direction, the ball is going up with a velocity until it is then going down with a velocity, and so it can't go from a positive to a negative without at its very peak hitting the velocity in the y of 0 meters per second, right there at that middle point. The other thing we can assume is if it is symmetrical, like most of these are, then you're going to be able to say things like the time for this first half is going to be equal to the time of the second half, okay? That can help us out a whole lot, because that means we can then solve things for when the ball is at that point where we know another velocity in the y for it. The other thing that I need to point out is that our y is our limiting factor, because it is the one where the acceleration is. Notice that if I had a velocity in my x direction, but no acceleration, it would just carry on forever. It's the y direction where gravity changes it and eventually brings it down to a stopping point. As long as we don't have a brick wall or something to stop it here, the acceleration doesn't affect it in the x direction, so it would technically carry on forever if there was nothing limiting it. And so it is our y direction and gravity and the earth which is limiting it. Okay, so this is the basics of what we need. Next time we'll look at how to do a problem with it.